Okay, for lesson 12.8, we're going to work in power series. Let x be a variable. Let x be a variable. In other words, we're going to see that x can very well take on different values. It's not a constant. X could represent all these different possible values. So a power series in x now has this additional form that you'll have a sub n, a formula that you've been seeing all along. But now you're going to throw powers of x into the mix. Notice also, we mentioned this earlier, and it's going to become very regularly seen, that our counter now will actually begin at 0 for most of these power series. So when we say a power series, we mean we're going to have a formula much the same way that we've been working all throughout these last number of lessons. But we're going to have a power of x as well. Generally, the first term that is seen, called the 0th term, will have x to the 0 in it. It will be seen as a constant, usually. And then we'll have x to the first, x to the second. The number out in front will be determined by a formula that we'll see, and it should look rather familiar. Well, here's something that is super important. A power series may converge for some values of x and diverge for other values of x. So with the appropriate choice of x, you could see, oh wow, this series actually will converge. And with a very different one, you can actually get divergence. So let's assume that this formula that we can generally see in front of x to the n, let's consider it to be the most simple and basic formula of all. Let's just say it's always a 1. Okay, it's always going to be a 1. And if that were the case, take a look at example 1. You'd say, I've got this power series, n equals 0 to infinity of x to the n. For which values of x does this series converge? Now, you can look at that and you can think, well, wow, this is so very, very interesting. As I begin to work this out, as I just begin to jot this down, you could say, well, plug in 0. First term, x to the 0, we'd say it's 1. And then we'd say n equals 1, that's x to the first. Plug in n equals 2, there's x to the second. Here's x to the third, x to the fourth. You get the idea. This goes on forever. I'm stopping at an nth term, but it doesn't stop there. It continues to go on forever. And the big question is, okay, so you get the pattern. When does this converge? Now, I do want to bring this up. Believe it or not, you've seen this before. And it certainly might not seem to be the case that you have. But I'm going to write up above, and I'm going to change my variable just ever so slightly. What if instead of having x, what if I said, well, it's a variable, how about I call it r? I'm doing that deliberately. And you'd say, well, it's the same thing. You get 1 plus r to the first plus r to the second plus r to the third. Wait a minute. Maybe seeing this new form with r, you'd say, wait a minute. This series is a geometric series. By the way, so is the one with x in it. You see that? If you saw this, you'd say, well, every time I'm going from term to term, I'm multiplying by r. Absolutely. For example 1, it's the exact same format. It's just instead of writing it with an r, I've written it with x. And you could say, okay, so what's going on here? Well, you tell me, did the geometric series converge? Answer, yes. When what? when the absolute value of r was less than 1. When the absolute value of r was less than 1. So we look at example 1, and we'd say this is a geometric series. This is certainly a geometric series, and we can think, so what's going on with this geometric series? You can say it converges when the absolute value of our common ratio, in this case, we write that as the absolute value of x, is less than 1. Now, guys, in Algebra 2, we talked about a way to solve this absolute value inequality, or at least you should have. What you would have learned is, this less than, it was sandwiched between 1 and negative 1. In other words, you're saying if you choose x to be between negative 1 and positive 1, you will have this series converge. So this is a power series, but every power series that has convergence on an interval like this will also have an additional question, and that is what is happening at the endpoints. Now, sometimes kids will say, endpoints? What are you talking about? I want us to check x equals 1. Then I also want us to check x equals negative 1. By the way, we're always going to do this. You're going to see when you get an inequality, where x is between two values, we're going to go a little bit further and say what's happening here. Now, when x is equal to 1, please understand this means that sigma is really looking at 1 to the n. That's your formula. Now, that means that you might have something that looks even quite silly at first. You can think, oh my gosh, 1 to the n. Holy smoke. The limit as n goes to infinity of 1 to the n, where this is not close to 1 for the base, but literally equal to 1. Notice the big difference we've had in the past with that section on L'Hopital's rule, where you'd have a 1 for a base raised up to the infinite power, but that base was only getting close to 1. This really is equal to 1. So if you multiplied 1 to itself all day long for forever and forever, where are you going? 1, which, by the way, that's not equal to 0. So what's happening here? We can say by the nth term test for divergence, this series diverges. Now, real quickly, you could say, well, what about when x is equal to negative 1? You'd say, would you look at that? You'd have virtually the same appearance, except now x to the n, you've got negative 1 to the n. And sometimes you can say, hey, that's going to, before you were adding up a 1 plus 1 plus 1 plus 1. And here you're saying start with a 1, add a negative 1, and then you continue to add this on and on forever. You think, well, what's happening here? Well, let's think about that nth term test once again. The limit as n goes to infinity of negative 1 to the n, pardon me. What's that limit going to arrive at? Doesn't exist. You'd be bouncing between positive 1 and negative 1. And that's not 0. By the nth term test for divergence, you're seeing the other endpoint doesn't work. So what are we going to do? For what values does x converge? I'm going to write this as an interval. We're going to say converges for x being an element between negative 1 and 1, not including either endpoint. Both of the endpoints fail. Sometimes one of the endpoints will work. Sometimes both of the endpoints will work. You really do want to check both endpoints. Okay? That being said, this is without a doubt the classic first power series that you're ever going to look at, especially since in theory you should study the geometric series in this class. But let's be very honest, when we talk about future problems, for example 2, we're going to attack this problem with the ratio test. The ratio test will be, without question, your go-to for power series. You're going to see that on the AP exam. FRQ after FRQ, when you get these, you will say, well, I'm going to start off by doing a ratio test. And let's go ahead and see what that would look like for example 2. Because again, they're saying for which values of x are we going to get convergence? Well, we're going to have to, work this thing out. We're going to say a sub n, of course, is just x to the n all over n plus 1, and then 2 to the n. But a sub n plus 1 would be x to the n plus 1 all over n plus 2 to n plus 1 power. So by this ratio test, we're going to say the limit is n goes to infinity. And by the way, kids ask this all the time. They'll ask, is it okay, instead of to stack the division, is it okay to just multiply by the reciprocal? The answer is definitely yes. You do not have to write an improper fraction, a complex fraction, a fraction over a fraction. You can essentially say, look, I know I'm supposed to divide the n plus 1 term, which will include an x now, and I'm dividing it by the nth term. But dividing by the nth term really means multiplying by the reciprocal of that nth term. Well, let's do a little canceling. The 2 to the n and the 2 to the n plus 1, that's going to cancel, and you're going to be left just with a 2 down below. The x's are going to cancel. You've got n plus 1 up here, and you're going to say, well, isn't this nice? I'm going to have one single x left up on top. I have n plus 1 terms of x in the numerator. I only have n down below. In other words, I have one extra term of x up above. Everything else gets canceled out. And now, if you're really on your toes, you're going to be able to help out with some n behavior too. What's happening with n plus 1 over n plus 2 as n goes to infinity? Where is that headed? To just a 1. So would you believe, look at this, I still have x in absolute value. By the way, that can bug kids. They'll say, Mr. Dobner, there's no negative 1 to the n. Why are you putting absolute value around it? Guys, x could represent negative numbers. Just because you don't see a negative out in front of x doesn't mean that x couldn't be negative. So always keep absolute value around x to the first power. You very well will need it. And then you'd say, well, wow, n behavior, the n plus 1 over n plus 2 just wiped out. Yes. When does this converge, though? By the ratio test, this converges when we are what? Less than 1. Always. Ratio test says your limit, when it's less than 1, you will converge. Hey, I'm going to solve this thing. I'm going to multiply both sides by 2. And then if we do a little sandwich, we're going to be between negative 2 and positive 2. Okay, so guys, we found an interval of convergence, but now what you must do is check the endpoints. You've got two additional cases, x equals 2, x equals negative 2.